Hello all, in this video we will look at various sufficient conditions that enable linear convergence of gradient descent. Let us take a look at some non-strongly convex loss functions that are known to exhibit linear convergence nevertheless. Consider the least squares loss function, which is given by half of norm square of ax minus y, where A is some m cross n matrix and m is less than n. You can easily calculate the Hessian of the loss function as A transpose A, which need not be positive definite if m is less than n. In fact, the Hessian is a n cross n matrix, but its maximum rank is less than equal to m. So at least n minus m eigenvalues are always 0. Hence the least square loss function is not necessarily strongly convex. However, it also exhibits linear convergence, suggesting that our assumption regarding strong convexity can perhaps be relaxed. Another example which is not strongly convex but still exhibits linear convergence in practice is the logistic loss function, which is given as the average over m quantities log of 1 plus e raised to power minus yi ai transpose x. In general, we can define the optimal set as calligraphic x star, which is equal to the set of all x star that minimize f of x. If the function is strongly convex, we already know that the calligraphic x star is a singleton. In general, however, that may not be the case. So instead of using x star in order to specify these conditions, we will use the projection of x to the calligraphic x star. We have already seen the projection operator. So let us define P of x star of x equal to arg min u over all calligraphic x star x minus u norm square. As you recall, this is the projection of a point x onto the calligraphic set x star, which is basically the nearest point in x star to x. Now by this definition, we have that f of x star is equal to f of projection of x onto calligraphic x star. And this holds for all x. The discussion about these weaker conditions is taken from these two references below. Please refer to them for further details. We list these weaker conditions. So all of these are implied by strong convexity, but the converse is not true. We will list them in an order so that they get weaker and weaker as we go on. So the first will be the strongest and the last would be the weakest or the most general. So the first is the essential strong convexity, which is for all x and y, such that the projections onto calligraphic x is the same. F of y is greater than or equal to f of x plus inner product of gradient of fx, comma y minus x plus mu by 2 norm square of y minus x. Next, we have the weak strong convexity, which is that for all x, we have fy is greater than or equal to f of x plus inner product of gradient f of x times projection of x onto calligraphic x star minus x plus mu by 2, the square distance between x and the set calligraphic x star. Third, we have the restricted strong convexity, which is that for all x, the inner product of f of x, comma x minus projection of x onto calligraphic x star is greater than or equal to mu times square of the distance between x and the set calligraphic x star. Next, we have the error bound for all x, which says that the norm of the gradient of f of x is greater than or equal to mu times the distance between x and set calligraphic x star. Then we have the Polyak-Lojasovich inequality, PL inequality, which we already seen, which is that for all x, half norm square of gradient is greater than or equal to mu times the optimality gap at x. Then finally we have the quadratic growth, which is that for all x, the optimality gap at x is greater than or equal to mu by 2, the distance between x and the set calligraphic x star. These are 6 common conditions that are used in the literature, and they have been well studied in the references cited earlier. However, there are a few more that are not covered. Actually, all of these can hold even if a function is non-convex. But strong convexity implies these. And in fact, we have already seen the proof of PL inequality. The others can also be similarly obtained from strong convexity. Although I've listed all these properties, this is just for a reference and you don't need to remember them. However, there is a lot of literature where people try to extend the results obtained for strongly convex settings to settings where only some of these inequalities hold. The Polyak-Lujasovich or the PL inequality that we have earlier seen is particularly interesting. Let us see if the least squares objective that we saw earlier satisfies the PL inequality or not. Recall that for the least squares problem we have that the loss function is given by half norm square of ax minus y. Suppose that the rank of A, which is a m cross n matrix, is equal to m, which is less than n, so that it is a underdetermined system of equations. So in this case you can see that ax equal to y always has a solution since the columns of A span the entire space Rm. Therefore, this loss function at x star is equal to 0. Therefore, to verify the PL condition, we need to verify that norm square of A transpose into Ax minus y is greater than or equal to mu times norm square of Ax minus y for some mu greater than 0. In other words, this condition implies that PL inequality holds for least squares. For establishing this, we can use the fact that A transpose is full rank m cross m matrix. And the smallest eigenvalue is given by lambda min of A transpose, which is also the square of the smallest non-zero singular value of A. So these allow us to expand the norm as Ax minus y transpose A transpose Ax minus y. And you can see that the right hand side can be lower bounded as lambda min of A transpose times norm square of Ax minus y. So this implies that mu is equal to the smallest eigenvalue of A transpose, which is also equal to the sigma min square of A, which is the square of the smallest non-zero singular value of A. The relationship can actually be derived from the eigenvalue decomposition of A transpose. In summary, we have seen that the PL inequality holds for least squares loss even though it is not strongly convex. In fact, PL also holds for a broader class of functions, and you have to look at the reference papers for more examples. Let us briefly look at PL functions, which are those functions that satisfy PL inequality. A general result that is proved in the reference cited is that for any strongly convex function g, the function f of x equal to g of ax is PL, where A is some matrix. We have already seen the examples of least squares, so this result already covers all convex quadratic functions. In general, any affine transformation on a strongly convex function might remove the strong convexity, but PL would still hold. The functions satisfying PL need not necessarily be convex. However, all PL functions are invex. Invexity is a property where if a point is stationary, that is, it satisfies gradient f of x star equal to 0, then that point is also the global minimum of f. Recall that this is obviously true for convex functions. So convex functions, whenever a point is stationary, it is a global minimum. And in general, this is true for a broader class of functions, which are called invex functions. Invexity is a more general property and holds whenever stationary points are global minimizers. If you look at the PL inequality, which is that half norm square of gradient greater than or equal to mu times optimality gap at x, you can see that if there is an x which is stationary, that is the x for which the gradient vanishes, it would imply that f of x star is greater than or equal to f of x. Now f of x cannot obviously be strictly less than f of x star because the f of x star is the minimizer. So the only possibility is that f of x equal to f of x star, which means that x is also the global minimum. So for PL functions, it holds that all stationary points are global minimizers. Therefore, all PL functions are invex. So here is an example of a non-convex PL function. The function is x square plus 3 sine square of x, and as you can see, it is non-convex. The function, however, satisfies the PL inequality. Linear convergence of gradient descent holds for PL functions regardless of whether they are convex or not. We make the following assumptions. A4 is that the function f satisfies PL inequality with parameter mu. For a function satisfying PL, x star need not be unique, so we have our usual oracle complexity bound in terms of the optimality gap. Recall that we defined the initial optimality gap as bf equal to f of x1 minus f of x star. Also define the condition number similarly as L over mu. Then we have the following result. Under assumptions A2 and A4, which is that the function is L smooth and mu PL, the oracle complexity is given by order of kappa log bf by epsilon for the choice of eta equal to 1 over L, which is remarkably similar to that we obtained for the strongly convex case, except that it is written in terms of the optimality gap instead of the square distance from the optimum. Further, the function may be non-convex here, but still the bound is specified in terms of x star, which is the global minimum as well as the stationary point. Let us look at the proof, which is actually very simple and involves only two steps. The first step is the same non-increasing function value that we used for smooth convex functions and also for non-convex functions. Repeating the exact same steps as earlier, we would write f of xt plus 1, which would be f of xt minus eta times gradient f of xt, which would be less than or equal to f of xt minus eta times 1 minus eta L by 2 norm square of gradient f of xt. Where recall that we use the quadratic upper bound for L smooth functions to get the inequality. Now, as earlier, assume that eta is less than 1 by L, so that 1 minus eta L by 2 is greater than half, so that the right hand side can be bounded as f of xt minus eta by 2 norm square of gradient f of xt. So this is exactly what we had derived earlier for smooth functions. Next step is to simply use the PL inequality for the gradient term here. So if we use the PL inequality, we would be able to upper bound the minus gradient norm square term and would get f of xt plus 1 less than or equal to f of xt minus eta mu times the optimality gap at xt. Now to get it in the form of a contraction bound on the optimality gap, let us subtract f of x star from both sides so as to obtain f of xt plus 1 minus f of x star less than or equal to 1 minus eta mu times f of xt minus f of x star. So then if we recursively follow this all the way through to the first iteration, then the right hand side, which is the optimality gap at xt plus 1, can be bounded as 1 minus eta mu raised to the power t f of x1 minus f of x star, and then using the definition of bf, this would be less than or equal to 1 minus eta mu raised to the power t into bf. Now this result would be meaningful only if eta is less than 1 by mu, but we have already assumed that eta is less than 1 by L, and because L is greater than mu, so 1 by L is less than 1 by mu, so automatically eta would be less than 1 by mu. In fact, this bound requires us to choose eta to be as large as possible, so we will choose eta equal to 1 by L. So the final linear convergence rate looks like this: f of xt plus 1 minus f of x star, which is optimality gap at xt plus 1, is less than or equal to 1 minus mu by L raised to the power t into bf. So this optimality gap is decaying exponentially with t. To get the required oracle complexity bound, we would then equate this with epsilon and take the logarithm on both sides so as to get t equal to 1 over minus log 1 minus mu by L times log of B by epsilon. In case we assume that the condition number is much greater than 1, we can simplify the oracle complexity and obtain the required oracle complexity bound of order kappa log Bf by epsilon. It is remarked that while the proof for the PL case was simple, such simple proofs for other conditions that we have looked are rare. As I said earlier, there is a lot of open problems where there is a need to generalize the result obtained for strong convexity to those using, let's say, PL or other inequalities. Let us summarize the results obtained so far. I am omitting all the constants such as L, B, Bf, mu and only keeping epsilon here just to get a perspective. We are considering only smooth functions and we will write down the assumptions considered so far, the metric corresponding to each assumption and the oracle complexity that we have obtained. We have seen the strongly convex functions for which we use the squared distance from the optimum as the metric and the oracle complexity was order of log 1 over epsilon. Then we saw functions satisfying PL inequality, which is weaker than strong convexity, using optimality gap as the metric and still achieving the order log 1 over epsilon oracle complexity. Then if we only assume convexity and use optimality gap as the metric, we were able to get oracle complexity of 1 over epsilon. Finally, if we did not make any assumptions regarding convexity, thereby allowing functions to be arbitrarily smooth and even non-convex, and use the gradient norm as the metric, we got an oracle complexity of order 1 over epsilon square to reach the stationary point. Just to see things in better perspective here, let us consider a simple example value of epsilon equal to 10 power minus 3. Then if we are considering log to the base 2, we can see that we require 10 iterations for the cases where we have linear convergence, that is for strongly convex and PL functions. However, we require 1000 iterations for minimizing general convex case and million iterations for non-convex setting. So as you can see, there's a lot of difference between these three regimes. So that is all for this video. We are done with our discussion on unconstrained minimization of smooth functions. In the next video, we will start looking at problems with simple constraints.